Hi, my name is Kate Woodland, and this is Lab 1 for Physics 2211 called Constant Velocity. This lab is designed to show Newton's fundamental laws in the real world. We were asked to observe an object moving at the same speed without changing direction. I chose to analyze a cart moving on a frictionless track, so the cart is my system. The track and everything else around the cart is its surroundings. This lab tests the accuracy of Newton's second law of force and acceleration. To do this, we are told to compare two position time graphs, one with data from the real world and the other from a computational model. Since the object is moving with constant velocity, we can imply that the net force of the object is zero. The object is not accelerating or changing direction, so it makes sense that the net force would be zero. The diagram shows the situation we are seeing in this lab. No force is being applied to the object in the x component. We are told that the system is frictionless. Gravity is acting on the cart, however, net force is still zero because the normal force cancels out gravity. In the previous slide, I mentioned that F net is equal to zero for this scenario. F net is equal to the sum of all the forces on the object, so with the diagrams it's very easy to see why it would be zero. But this can also be proved mathematically through equations. According to Newton's second law, F net is equal to mass times acceleration. Acceleration can also be described as v final minus v initial over delta t. In a situation where velocity doesn't change, v final minus v initial would result in zero. This makes the whole right side of the equation zero, so therefore F net is equal to zero. Other equations used in this lab were the velocity update formula and the position update formula. In each of these equations, I made some substitutions when doing the math. F net divided by mass is the same thing as acceleration, and average velocity is equal to the initial velocity plus the final velocity divided by 2 when F net is constant. When I say that F net is constant, this means it could also be zero. To collect data, I used Tracker, a video analysis website. I imported my video of the cart moving on the frictionless track and set my axes, seen as the purple lines. I set the time frame of the video to be just between the two black triangles at the bottom of the screen. I chose a time frame in the middle of the cart's motion to ensure that it would have constant speed. Next, I selected about 20 different points along the x-axis. This then produced a position versus time graph as seen in the right-hand corner. There is a clear positive correlation between position and time, so it produced a positive linear graph. Using this graph, I found the average velocity. I chose two of the points and plugged them into the average velocity formula and got an answer of 456.38 meters over seconds. It should be noted that these units are not accurate for the video, but it produces the correct theory. It should also be noted that the slope of the position versus time graph is velocity. If you were to graph the slope, it would produce a horizontal line. This implies that velocity does not change magnitude or direction, corresponding with our goal of an object with constant velocity. To form a computational model, I used GlowScript, a Python-based website, to write the program. I set the ball's mass, line 32, to be 1 just for the sake of simplicity and because the mass has no meaningful effect on velocity for what we are concerned about. Next, I set the ball's initial position, line 35, to be 0, 0, 0. The initial velocity can be found in line 36. The velocity is set to 457, and it's important to notice that only the x component has a value. This is because the object isn't moving in the y or z direction, so its position and velocity are both 0 for y and z. Delta t is set to 0.01 to gather new data points every 0.01 seconds, making the graph perfectly linear. Next, I plugged in the amount of time I wanted the graph to display, which matches the time I found using Tracker. This time was 0.67 seconds, and I plugged this qualification into line 49. As seen in line 54, F net should be set to 0, 0, 0 because the object is in constant velocity. The next thing to do is to sub the velocity update formula, line 58. With what I previously said about F net being 0, this equation quickly turns into final velocity equals initial velocity. This guarantees the position versus time graph will be linear. The position update formula is written in line 60, showing that the position on the cart increases by a factor of 457, the velocity in the x direction as time goes on. Here are the two graphs that are produced from all that coding. On the left, we have the position versus time graph, and on the right is the velocity versus time. It's easy to make conclusions from these two graphs because they are very neat and don't include any type of experimental error such as unwanted friction. Here are the two sets of data plotted on the same graph with position on the y-axis and time on the x-axis. As you can see, the experimental data from the video put into Tracker is slightly off from the computational model data. The computational line basically shows what we predicted for this experiment. It shows the line if the experiment had gone 100% correctly. The data that I gathered shows the same concept as the computational data, the concept being that velocity is constant and F net is 0 for the system. The slight errors are probably due to unwanted friction. The cart and track don't demonstrate a perfectly frictionless scenario, but it's pretty close. To fix this, I could have picked a system with a smaller coefficient of friction, or I could have adjusted my equation to consider friction. This, however, would potentially distract from the idea that the net force is equal to 0. If I were to flip the axes, my results would look something like the graph above. I would use all the same data points and the magnitude of my average velocity would remain the same, but it would be in the opposite direction. This situation still demonstrates that the object has a constant velocity, 0 acceleration, and 0 net force. While it's easy to conclude that the net force is 0 in my model, it's very difficult to say how many pushes and pulls are added to produce 0. Many forces are impossible to see with the human eye, such as friction or air drag or wind. All of these had very little effect on my specific system because the environment was fairly controlled, but it's still very hard to actually count these forces. An object with constant velocity means the object's speed remains the same and the direction stays consistent. Speed is actually the absolute value or magnitude of velocity. So with direction constant also, it makes sense that velocity remains the same. An object with constant velocity also means the acceleration is 0. We can think of this graphically and mathematically with calculus. A graph of velocity versus time with a constant velocity is portrayed by a horizontal line with the y-coordinate remaining the same at the value of the velocity. If we take the derivative of a constant number, you get 0. Acceleration can be found by taking the derivative of velocity, so therefore acceleration is 0 for an object with constant velocity. As stated previously, F net is equal to mass times acceleration. When acceleration is 0, so is the net force. Finally, this lab shows us the difference between predicted models and models created from the data in the real world. The predicted model shows the results of a perfect scenario. The real world data shows human error and experimental error. While this data may not be perfect, it typically portrays the main focus of the hypothesis well. That's it for the lab. Thank you for listening.